Yeah.
No, no. Fuera.
Okay, so our next lecture is by Bill Lee, who actually was here at Center of Frontiers for Nuclear Science for many years, I guess, and participated in the organization of multiple schools here. But now he's here to present forward physics at the Electron-Ion Collider. The floor is yours.
Yeah, thanks, Alexei, and thanks, Fred, to invite me back to the kind of the great room that we have at the CFNS. Very excited to talk to you, to talk about something that the forward physics, which is a very exciting subject. You will hear a lot about it. But in the same time, I know enough about it to know that this is a very misleading word. I'm very worried that if you just take this word and run, and in the future you may run into some, let's say, pitfalls. So the first thing that we're going to do is to define what do I mean by forward, right? It's forward physics. You heard so much about. You probably heard about the far forward physics, far forward region of the EIC, and also then there is also a scattering, that is particles going forward. We're going to clear all of that as the first part of this lecture. Then my hope is that I can imprint some of the EIC geometries into your head, whether you are theorists, theoretical physics students, or experimentalists. I want to kind of take you into the EIC geometry, and so you understand what this forward means. And of course, if there's a forward, there has to be a backward, right? So everything has to be symmetrical. So then today, last part, I will take you, whether you are from the, let's say, the hot QCD community, cold QCD community, whether you are doing some experiment at CERN for your PhD or Brookhaven or Jefferson Lab, there is a common language that we're going to use for EP scattering is from now into the future. So I hope to kind of introduce you to these languages so we understand in the future what we are talking about. So I know that my student Zakia, some of you have been asking her, hey, what is your project? I don't know whatever she said, then this should be her project. And this is called the backward angle neutral pion electron production above the resonance region at Jefferson Lab Hall C. So this should be the topic, and many of you look at this go, I have no idea what this means. So the second hope of my lecture from day one is that I hope that by the end of the lecture, you'll be able to understand, parse this into a human language, in the language of physics that you understand it. And then you will look at this title again. So this just doesn't appear to be so encrypted. So day one, this is a typical exponential learning curve. We're going to cover this part here, which is we're going to go slow pace, start with something this simple. And then day two, I hope that we're going to run into EIC physics straight directly to look at some examples of this forward physics and also the forward physics goals. And also, we have the far forward instrumentation, then some examples, some operation challenges, then we draw some conclusive remarks. So then that's day two. So it's the kind of the pace of the kind of knowledge picks up. Notice that there is something in the missing. Day one, this is day one, and this is day two. Oh, sorry. You see here, there's a middle part that is missing. I know there are lots of repeated kind of knowledge, and some, for example, the parton, generalized parton distributions, or the parton distribution functions. Those knowledge, I won't cover those. I think this is probably, you will probably have a flashback from some of the greatest experts like Powell and others that they talked about it already, so we won't waste time a lot on talking about that. So the word forward is, in my opinion, a very problematic word, right? So if we have a forward, then we really have a backward and also the middle part. And what do we mean by that? So you can see it's forward physics at ESC, right? So we all know that the proton is not really a structureless particle. So it's almost like this elephant. The direction that you approach this elephant matters a lot, right? So for example, this guy touched the trunk of the elephant and go, oh yeah, this looks like a snake. And then if you look at the horn and say, oh, this looks like a spear. And if you look at the legs in the middle part, we said that must be a tree. So the direction really matters a lot. So there are two forward in this context here. So in the scattering physics, if we have a projectile A, then coming towards a target B, then they have a collision. And then I have an ejectile, which is whatever being knocked out. Then we also have the ejected target or recoil targeted. Look at it. So in this kind of regime, you kind of see what is forward here. But let's actually take this to a proton rest mass frame where we have the A coming in, B as your target, and then you can see clearly then the ejectile C being knocked out into whatever is the direction of the incoming projectile A, and we define this as a forward, right? So then whatever this area would be the backward. So this is what this means in the scattering experiment. So that the fixed target experiment, what forward means, and here's what backward means. But in the EIC, it's not quite so. So EIC context. So there is a dual meaning of the word forward. I will get into why very soon. So we just talked about what the forward means in the scattering regime, where the scattering experiment. This is basically the phase space or the physical space that is covered by the region that is in the direction of you, like your projectile, and then after the interaction, then this space basically defines forward. And then at EIC context, forward means something different. At the EIC, the forward refers to the hadron going direction, where the outgoing recoil proton, neutron, and the nuclear fragments that is detected by the far forward detector system. This is the forward in EIC. To put that into perspective, the EIC as we know it is this ring plus epic detector over here. So then the forward means the positive X direction. Oh, sorry, positive Z direction. Of course, the Z normally means that is along the beam, whether it's Jefferson Lab or the EIC or CERN, is that the Z axis normally defines as the direction of the projectile or your electron. But in this case, no. This is the left epic detector. And the Z axis is actually in the opposite direction of your electron. The electron being con this like this, and then the positive X points this way. And then the X-axis points to the center of the ring to the left, and then Y-axis points out. So this is the geometry of the epic. And the forward means that it's whatever that is going forward in the hadron going direction. Here, I want to just for you to not to be deceived by this picture here, because the central epic detector is parallel to the electron beam, where in this picture is not quite lined up like that. Yeah. Any question about this? Of course, we use the rapidity y and also the super rapidity eta to define how forward things go. Okay. I think this missing a slides here. So actually no, I didn't. So so rapidity and pseudo rapidity, what are they? So then the rapidity is defined using the particle energy and also the longitudinal momentum of your beam. So rapidity is defined as 1/2 log E plus momentum over the E minus momentum. And the beautiful thing about this particular quantity is that when you have absolutely no Z direction momentum, the longitudinal momentum, where your particle is traveling after the interaction transverse to your beam momentum, and then this rapidity value will give you 0. And then if there is no transverse momentum, or this your beam, your particle going in collinear with your beam momentum, and then this rapidity give you infinite. And if it is the opposite side, the rapidity is negative. The good thing about this, physicists like it, is that the Lorentz boost along the beam axis or the rapidity shift by a constant. And the difference in rapidity for a particular, let's say, value is Lorentz boost invariant. So it's actually does not depending on which reference frame you are. So this is good, but what's better is actually pseudo rapidity, which we will talk about a lot in various of the detector coverages. So then the epoch loved the pseudo rapidity because it only concerns the emission angle after the interaction of your particle eta with respect to the beam axis rapidity, which is this equation here. And then because of the rapidity approximate to the true value of the rapidities, this is the pseudo part, is that the rapidity is almost the same as pseudo rapidity is almost the same as the rapidity when the particle, the beam energy is much higher than its mass, then this two value approximately equals. And we prefer this because it's kind of simple. This is an example of the CMS detector schematic. If you look at the rapidity, we remember we talked about the eta or the rapidity or the super rapidity 0 when the particle is emitted perpendicular to the momentum, which is the beam momentum is this direction. And then you have a pseudo rapidity of 0 when these eta is 90 degrees, right? 90 degrees. Then this value is 1 if this this theta is 45 degrees, and then it's infinite if when this theta is 0. So it's very simple. Hope that you will remember these three values. Once you see a, let's say, an epoch detector coverage like this, you say, I recognize this. The central detector coverage is eta of larger than minus 3.5 and smaller than the minus 3.5 and smaller than 3.5. I said, okay, I know that eta of 1 is 45 degrees. 3, this is probably 120 degrees, give or take, right? So this eta is very, very simple to remember just because of this very nice relationship over here. So by looking at this epoch detector coverage, you see this, okay, this is all very nice. Then why don't we use 45-degree angle as a boundary, right? Because if you look at the forward and end cap coverages, it's actually 1.5 and beyond. Any guesses? This is actually one question that you are forbidden to ask. We will talk about it in the discussion session, but I think this is common. So if you actually ask a lot of people, then they give you different answers. But we can talk about that in the discussion session. Why this is not 45-degree. This boundary line is not used like the CMS over here. Okay. So I think we talked about the experimental coordinates of the EIC, X, Y, Z. I hope that now you have a better understanding when we talk about the X, Y, Z coordinates, what is what at the EIC. And we talked about what is forward and how the forwardness is measured using the pseudo rapidity. And here is the problem is that, or here's a little bit of a dilemma, is that the EIC have a crossing angle of 25 milliradian because for very innovative reasons, I will talk about it. And this actually bring our definition of let's say, the forwardness to a little bit of a complication. If you recall that there are two problems here, is that our definition of the forward is a little bit against the convention because if you remember in this picture here, the proton is the target and electron is the projectile. And the forwardness should be defined by the electron direction. But in the EIC case, we did the opposite. Make sense? Second is that the proton direction is a 25 milliradian off the axis. So if you actually use eta as this definition, CMS, there is no crossing angle. But for the EIC, there is a crossing angle here so that eta infinite is not along the axis of your beam or the experimental coordinates. So be very careful about this when you do the analysis. Make sense? You probably need a little bit of a time to digest this, but we will see examples after examples in the remaining part of this lecture and also the next lecture to understand this a little bit better. So let me just say one last time is that eta of infinite is not on the axis, is not in the positive axis of our experimental coordinate. There's a 25 milliradian difference. And in terms of phase space, that's a huge phase space if we consider the Lorentz boost. Okay. Consistencies, dilemmas, who is going to fix this, right? Of course, identifying the problem is one thing. Then we need a workforce to remember these problems when you instruct your students when do the EIC analysis. And I'm looking at the people who is going to fix this problem and remember it in the future. Okay? All right. Quiz on the special relativity. So if I have an electron here coming into a proton target, then imagine we have an elastic scattering where the electron scatters off and then the proton is nudged or recoiled in this direction. This is the proton rest frame. And if I give a boost of reaction, this is almost what we have at JLab, right? And if we have a Lorentz boost in the direction of the negative electron momentum, which is in this direction here. So which one of these options is correct? What should I see? Any guesses? Any A's? Very good. C is absolutely the right answer, right? This is what we have at the EIC. If you want to take your JLab experiment and you want to see what you have at the EIC, all you need to do is to basically, in your head, draw this picture, in your head, draw the Lorentz boost, then immediately you have the EIC picture. And this will help you to understand exactly where things actually ended up. So this is exactly what we have, right? EP scattering, electron coming in, meet the proton at the interaction region. Then, of course, protons flies out and electron scatters in the other direction. And this would have been the EIC design if it was designed 30 years ago. Notice that the proton and the electron, there's no crossing angle, they are head on. Why do we do that? If you look at the beam, they are not continuous, they come in batches, like bunches. Bunch number 1, bunch number 2, etc. Then imagine this is the proton bunches in the blue, and then the other electron bunches. And then the interaction happens when the two beam bunches kind of overlap. Imagine this one moving this way and that one moving that way. So you say, oh, okay, overlap, right? Look at the overlap. You see the beam are not completely overlapping because they are actually oblong. They're not a circular, right? If you overlap this, you basically only have 50% of the probability that they will actually interact, right? So how do we maximize this? Then the idea here is that we make them head on. So we reduce the angle, the crossing angle, and then they can actually come in and interact. There is a higher probability of overlapping. We reduce the crossing angle so that they can come in more parallel and more higher probability overlapping, right? Good idea. So that's how Hera designed their electron-proton collision interaction point about 30, 40 years ago. They had about 5 milliradian of bunch crossing. Of course, there's nothing like absolute, right? I mean, how do you have two beam type completely make everything head on? The significant drawback is that the particle, the advantages is that you maximize the overlap, and then you maximize the luminosity. But then the drawback is that the particle remnants overlaps with the incoming electron beam. What if you actually have particle that is created exactly along the direction of the electron beam pipe? You won't be able to see it, right? Because you can see that depending on the proton momentum, this forward region is compressed during Lorentz boost. And then your electron beam is right inside of your acceptance. You can't really detect all of the particle remnants. So then EIC have fixed that. There is a 25 milliradian crossing angle. There is more space that we can put detectors around the proton, outgoing proton direction, the electron and the proton beam of pi. There is a clear separation of the two, so we can stuff more detectors inside. We'll talk about that in the next lecture. And then you'll probably will ask, okay, what about the beam crossing bunches? Then how do we resolve this problem? Don't we have a reduced luminosity? That's where brilliant people like Chris yesterday, that I don't know if he talked about the crab cavity. So then what happened is that when the beam is transported, when it gets closer to the interaction region, they use something called the crab cavity to wobble these beams. So they start to wobble this direction, and then they start to wobble the other direction. They kind of oscillate. And then when they get to this interaction region, they exactly overlaps. So this is a very, very beautiful technology. And this is the single most, I think, the innovative part where we can have our cake and eat it too. So yeah, it's very nice. So of course, when you transport the beam, you have another crab cavity to wobble things back and to make sure that the beam is transported longitudinally. Any question about that? Okay. And how many of you are from S Phoenix? Or are familiar with S Phoenix? Or worked on Phoenix or S Phoenix? Okay, none? Okay, that make me happier. It doesn't break your heart. So we know that there are two detectors, Star and S Phoenix. Both have retired due to the shutdown of Rick. Then there is a question from their students or postdocs says, hey, we spent a long time building the S Phoenix detector. These are beautiful state-of-the-art detectors, and why can't these be used for the EIC? Why do we have to spend like hundreds of $millions to build something new? So if you look at the S Phoenix detector, and if you look at how things collide, they have a proton-proton collision or gold-gold collision. So then what happened is that they will come in and collide. Their forward and back is exactly the same phase space because this is the center of the mass collision frame. And then most of their particle will go to the central region, like in this cylindrical region in the middle. So these regions here. So this is why they optimize the particle detection in all the central regions here. They have the several layers of trackers. I don't think they have PID, but they really does the tracking of the particles well. They do PID that way. The drawback is that they don't have anything in the cap. If you look at the EIC, EIC is in fact a scattering experiment where we have a proton momentum heavily boosted into one direction and then electron going the other direction. So most of the particles, especially the electrons, will end up in the cap, the forward and end cap. And you can notice that there's nothing in S Phoenix to detect the electron. And not to make matters worse, all of these detectors need readout, coolings. Like so we know that cooling requires water. So you have a huge material budget in this area so that it really makes S Phoenix not very appealing as a detector for the EIC, because you will have a horrible electron detection efficiency and also a reconstruction of the energy and momentum. Make sense? Let's go to a little bit, revise a little bit on the Rutherford scattering. So I know that Con and others probably talk a lot about it, but I just thought I'd add a little bit of flavor, tell you a little bit about some of the interesting part that I didn't even know as a student. So Mr. Rutherford had multiple graduate students. So how this experiment was done, right? It was that you have, of course, alpha particle collide with the gold foils. And then this experiment was really done with a scintillator detector screen that is all around. And we always say that, yes, when the alpha particle bounces and hits the screen and there is a spark. But little do I realize when I read this into it a little bit, it's a spark of light, right? It's not like there's no sound. So imagine you as a graduate student doing this experiment. What you are really doing is with a microscope and a counter and rotate the microscope in the very dark, looking into a piece of scintillator, looking for a very tiny spark of light. There is no sound. Yeah, it's just very difficult, right? So there are only two types of supervisors, as I always tell my students, is that there's one that the ones that says, I suffered as a graduate student, you have to do worse. And there's also other ones like Geiger. Geiger was one of the graduate students of Rutherford. He said, you know what? I'm not going to make my students suffer, so I'm going to invite a Geiger counter so that there is actually sound when you actually have ionization particles. So yeah, this is just a little bit of joke. So one part that I want to mention is that it's very interesting that there are particles, alpha particles, that hits the nucleus or get close to it, and then it will scatter forward. And of course, this direction defines the forwardness. And there's also a lot of backscattered alpha particles, and they are equally important. And it was Geiger and also a few others that, despite his supervisor said, hey, don't waste time on these regions, just forward, concentrate on forward. They said, oh, let's rotate the oscilloscope and see what happens, or the scopes to the back. And it's very interesting that they found something that is amazing. The forward scattered alpha particles, you can actually get the structural information of your gold atom, and the backward information is also very important because you get the information that this is something that is harder than your probe, and your probe bouncing right back. So this is very, very important for us to remember that the full structure of whatever you are measuring takes both the forward and the backward scattered processes to get the complete picture. The significance of the Rutherford scattering is really, really cannot be underlined more than it's really, I'd say many of the modern experiments still retain the same, let's say, either the technological, let's say the methodology, or the theoretical interpretation toolkit developed for this measurement. As an example, the scintillator material innovated to measure this. It's still used for many experiments today, as I will give you an example that our far forward region instrumentation scintillator material is very, very important. Then we also have the differential cross-section description from the Rutherford scattering. And there is a formalism which you will see in detail in next part. It's just very nice experiment, very nice experiment that we still benefit from today. If we look a little bit closely on the formalism, and you will see that we have something called the impact parameter. And that's something that is very interesting, because impact parameter, this is the definition of this, is that this is the distance, or the transverse distance of your probe, how far it is from the center of your target. And of course, the E is the center of mass kinetic energy, and also the eta is the angle. There's a direct correlation of your impact parameter to your angle through relative relationship. Of course, the energy is also in there. So the impact parameter is small, then your theta angle is larger. It means it bounces harder. And then if your impact parameter is large, of course, your theta is very small. And we still have some version of this for the EP scattering, as you will see very soon. So of course, the head-on collision impact parameter is 0. Then the minimum radius, it can be calculated just by recomputing the Coulomb energy formulas. So what about our EP scattering? So EP is almost like hit a watermelon with a bullet. Of course, here, our bullet is not electron. I hope everybody knows that. Then what exactly is our bullet? If it is not electron, of course, it's photons. There are two types of photons. We have the real photon, then we also have the virtual photon. So the difference is that I hope we kind of become appreciative that is that the virtuality of the real photon is the q squared of 0. We'll define q squared very soon. And then it is directly detectable, and it can only be transversely polarized. And interaction that involves a real photon probe is called the photoproduction. And then, of course, the virtual photon, the limit is that the virtuality, or you could say the mass of this photon, is non-zero. It can be space-like virtual photon or time-like. I hope you all know that. If you don't, that's okay. This is the first time you hear it, that's okay. It can be transversely polarized or longitudinally polarized. And this is important because we'll talk about the Rosenbluth separation in the second lecture, which you can actually separate these two contributions. And then the interaction involves virtual photon is called the electroproduction. Of course, the time axis is such, and here is an example of this such interaction. So here is a kind of a diagram for our virtual photon exchange for the time-like and the space-like interaction. Here we have the time direction, the space-like virtual photon, the propagator direction of this propagation is directly perpendicular to the time axis. And then time-like virtual photon is along the time axis. And then it depends on the value of the virtuality, then this space-like or time-like. So at the EIC and also JLab, we always deal with the space-like virtual photon. And for the collider experiment, it's often that we're referring to this kind of exchange as the time-like virtual photon. So here is an example of a professional EIC expert question. Yes.
Reason as to why in DIS we always choose a time-like virtual photon, or is it just a convention that we have taken?
So in the DIS, depending on what experiment you are looking at, the time-like virtual photon is almost often in the kind of the annihilation processes. So for example, if you have electron and a positron collider, almost every single particle that you're creating is all due to the exchange of the time-like virtual photon, because that's the q squared of it. If you compute, for example, the q squared, the small q squared is larger than 0.
In DIS, it's space-like, right?
Yeah. So in the EIC and also Jefferson lab, there's no annihilation. It's always exchange of these virtual photon, like tangential or perpendicular to the time axis. And this the large q squared is always larger than 0. Yeah. Maybe did I label this wrong? Yeah, I think I labeled this wrong. So the large q squared is always larger than 0. Yeah, so there's a typo here. I blame ChatGPT because it generated this with ChatGPT. I think I have the ChatGPT did the label wrong.
No, this is correct.
Oh, this is correct?
Yeah, it's correct.
The minus outside. The minus sign. Yeah, okay. That fixes it. Yeah, ChatGPT did generate this part wrong. Notice that I have to put a minus sign over.
So is it like when there is an photon exchange, it's always space-like? I mean, how do you say that? I mean, how do we know that? That's what is my question. Is it just a convention or?
No, so you compute the q squared first. If you're not sure, you always compute the q squared first. And then depending on the q squared value, so then how do you compute q squared? So you see you have your electron coming in, you know what your beam energy is, and then you detect your electron energy after scattered. Then you compute the forward momentum transfer, And then you will see if this is larger or smaller than 0. So then that's the process. They said, okay, and I can bet money that most of cases you will see, I'm looking at the space like virtual photon. In most cases, for the electron-ion collider, and also for Jefferson Lab experiment. And people could argue, what about TCS? Let's not worry about that. So here, the reason why we went through all this loop very slowly is that I want to show you this slide on a professional presented a XYZ meson production as an EIC feasibility study. And notice that this professional had a virtual photon here, and he clearly labeled photo production amplitude, right? So this could cause confusion. So another thing I want to caution you is that if your supervisor or other people says, hey, why don't we look at the photo production at EIC? Well, he or she may not be necessarily wrong. There is a subtle detail, so we will go through these. So the photo production at the EIC, one thing is for sure is that there is no real photon beam at the EIC. This absolutely not yet happened, or it's not going to happen at the project. So then what does the photo production mean here is that, well, the small q squared is not the same as q squared of 0, but the exact limit, the q squared limit where the longitudinal components of the virtual photon will vanish, and it will start to behave like a real photon. That limit, we don't know it yet. It could be 10 to the power minus 3 GeV. It could be 1 GeV. It could be 10 to the power minus 6 GeV. It could be 10 to the power minus 9. We don't know that. So that is something that we need to still have to explore at the electron-ion collider to see that when does the virtual photon start to behave like a real photon. So when, let's say, a person talk about, let's say, the photo production of something at the EIC, what he or she really means is the q squared is very, very small. Make sense? Pitfall number 2. So remember the Rutherford scattering, we have the impact parameter. We also have the energy of kinetic energy of the incoming alphas. And we also have the angle as a parameter to parameterize our formalism. And what about EP scattering? We also have a set of parameters. We have the Burican X, we have the W, the Q squared, and also the Mandelstam variable T. I think that Con talked about some of this, and we'll rush through this rather quickly. Let's talk about the Mandelstam variable T, because I think Con talked about that, but I also want to bring your attention to Mandelstam variable U. That is something that you probably didn't appreciate. So there are 3 Mandelstam variables. We have the Mandelstam variable S, and this is a big brother to our invariant mass. W is basically square root of S, and that is the total invariant energy of your incoming probe. Then consider that with the target. Then we also have a Mandelstam variable T. That is your target for momentum transfer of your target before and after the interaction. Imagine that you are a very heavy target and somebody come in and nudged you. And you said, I'm not moving. That means that your T is 0 because the for momentum transfer here is very small. But then what if you somebody nudged you and you fly off like crazy, right? So in that case, your momentum transfer or your form momentum transfer is very large. In that case, that's actually where the Mandelstam U come in. So when that start to happen, where somebody come in nudge you and you fly off like crazy, in that case, your Mendelssohn variable u is very small and your t is very large, right? So depending on which one is closer to 0, then you have the u channel or the t channel process. So we will talk about that also in the second class. So why do these invariant mass, there's Mendelssohn T, and also these what we call the language of the EP scattering, very important. Here I'm giving you an example. When I say that I'm measuring something above the resonance region, what do I mean? So here is that differential cross-section as a function of W from 0 to 4 GeV. If I want to see inside of the proton, I want to see the parton distribution of the proton, and then I ask you to develop an experiment, you probably won't develop an experiment with a W in this region because there are lots of resonances, right? You want to actually say, okay, above 2. So in these regions where the resonances are small, a kind of a plateau-ish. Of course, the higher the W, the better. Make sense? This is why the W is very important. When you have a result, you want to take a look at what is the W of that result. Is this in the resonance region? Are you sensitive to some resonances to give contribution to your signal? Or is this actually in the plateau region where there's no contribution from any known resonance is contributing? And of course, the Burken X is very important. I'm sure that some experts talk about that. And depending on where we're probing in the Burken X, what region, and your proton structure will look completely different. It can look completely like a gluon fusion, so, or a soup of gluon and a very bright, or you could have a medium energy where you have a hint of a valence region, or you have at Jefferson Lab valence quark region. It really depends on what kind of Burken X that your experiment is probing. So if you talk about Jefferson Lab, then basically that name by itself kind of fixes your coverage in your Burken X, right? It's in the valence quark region, which is around 0.3. Then Q squared is also very important, is our resolving power. As we know that the higher the resolving power, the lower the wavelengths that we need. So here I give you 2 examples. This is the F2 function, F2 structure function as a function of Q squared. As you can see that this is not all a plateau. There is a structure to it, depending on which Burken X you are. And here is the pion form factor experiment, which we will talk about in the second part of the lecture, where you can see that the data is up here, where the hard QCD prediction or the PQCD prediction is over here. We know that PQCD works at very large Q squared. And when is the data going to come down to meet this correct contribution? So this is something that we also had to find out. When is this data start to come down to the PQCD prediction? We don't know. So that is something that we also it's very important for us to understand what Q squared are we measuring when we're doing the experiment. Of course, if you say that, what exactly is the Q squared that I can see inside of the proton, I have a typo here, is about with proton size about 1 Fermi, and that corresponds to a Q squared higher than 102 G. Another very nice thing about our, let's say, these parameters, these kinematics variables, is that they are all Lorentz invariant quantities. So if we have, let's say, our theory friend predicted some cross sections, then we normally they will say, hey, what do you need? You say, I need a differential cross section. They say, which one? Then normally you would choose d sigma dt. The beauty of that is that your friend could actually compute this in the center of mass region. I mean, this is where most of the model are calculated, right? So then he or she doesn't have to Lorentz boost it to the lab frame. And you can actually directly measure this d sigma dt because this is actually Lorentz invariant quantity. You can directly compare the results. Make sense? These are all Lorentz invariant quantities. It doesn't matter which reference frame, these quantities stays the same. So that's why that the Jefferson Lab d sigma dt experimental results can be directly compared with the experimental results at the EIC if they are all d sigma dt. Make sense? We don't have to do the Lorentz boost. So there is something that we have learned the language of the EP scattering. Of course, we have to brush on that and we have to revise that. Here is a kind of when I took undergraduate students, my astronomer professor says, you know, imagine yourself listening to some lectures on star formation. And you absolutely did not pay attention in the class, and you didn't know what's going on. And then, but you want to appear to be intelligent, and then you paid attention, and you want to impress the presenter. What would you say? You have to ask a question. So then he or she, well, he said that you will ask this question. What would be the result difference if there is a magnetic field present in your results? Right? So that sounds intelligent, right? So that's going to fool people. So we also have such list. If you were looking at these interactions, you have no idea what they are. You said, okay, so what question should I ask? You can ask about the kinematics. You can ask, what about the probe? Is it a real photon or is it a virtual photon? Or you can ask about the time-like or space-likeness, etc., like she did. Or you can ask, what about which parton are we sensitive to? But this is the killer here. You can ask, what happens if your target or the beam is polarized? That will solve the problem. So just if you don't remember any of that, just remember the last. Polarization. So, okay, so I think now we can summarize. We talked about the dual definition of forward. I hope that you all confused. Very good. We can talk about it maybe in the discussion to unconfuse yourself, as long as you remember there's a problem with the forwardness. Forward in the scattering experiment does not mean the forward in the electron-ion collider and vice versa. There's some problems with the definition, and there's a misuse of photo production in the EIC. When you see this result, don't freak out, especially the one from Jefferson Lab. Yes, it does not get a real photon beam yet. Then we brushed up on the language for preparing for the second lecture. So we see eta, for example. We know what that means, right? And also that we had the list of the particle list that you will fool any particle physicist, pretend that you listen to his or her lectures. Then the last thing before we all go for lunch is that I want to come back and brush up on this particular thesis title. So remember, Zakia's thesis title is backward angle neutral pion electron production above the resonance region at Jefferson Lab Hall C. So does that make a little more sense now? So the backward angle means that the particle emitted comes back, right, upstream of the target. The neutral pion is pi 0. Electron production means that our probe is a virtual photon. Above the resonance region it means that its W is above 2 GeV. Jefferson Lab define the word Jefferson Lab defines the Brook and X. And then Paul C means that the fixed target spectrometer experiment have axis larger than Q squared, larger than 1. So this is really translated kind of a title. I hope that you now have a little bit of a kind of a to remember that of course what this language means. And I have to apologize that the field has got so specialized that the message are hidden, or many messages, hidden messages, is encrypted in such title. Of course, this is my thesis title. Okay, thank you very much.
Thank you, Bill. Questions? So, forward physics, case your target was polarized. Seriously.
Right.
So I'll give you my definition that I use. Let me know if it resonates. But then I think about lepton nucleon scattering. I would think about the lepton, which is the beam of lepton. So therefore, whatever follows lepton, this is what I would call beam fragmentation region. Whatever the proton is, for me, would be always the target.
Oh.
And if it's stationary or if it's moving, it doesn't matter.
Right.
So whatever skips the lepton and doesn't interact with the lepton, for me, would be the target fragmentation region.
Yeah.
That is what is, I guess, forward.
That's absolutely right.
And you say intermediate, so
so
touching on the task of the elephant. Because these two things, they are colored objects, they hadronize. And they have to be connected by some gluon fields and ultimately lose color. And therefore, in the middle of these two, unless I have Pomeron exchange, which I suppose I don't because I have a lepton exchange, or sorry, the photon exchange. So I don't have the rapidity gap with no particles. I have those particles which are hadronization of this soft field, which connects these two things.
Wow.
And for me, this would be the central region.
Wow.
Therefore, what I expect, like in my sort of brain of the theorist, in the rapidity plane, I would expect some sort of peaks and then some plateau populated by particles.
Right.
And so this is how I would characterize this. Thanks.
Yeah. So the sad thing about this is that I agree. Everything that you said, as you said, I agree. So in fact, I would address this with the physics examples specifically to address this kind of observables. Is that sadly, in both cases, by the EIC definition, they are both characterized as a forward physics. In one case, your target fragmentation that fragments forward in the direction of your target momentum, those fragments will actually be detected by the forward end cap and the far forward region detector stack. In the case where the fragmentation region, where you have electron knocking out just a piece, let's say there is a color exchange, a quark exchange. So in those cases, the proton won't lose too much momentum so that they will actually fly off in the central region. They will still end up in the far forward region or the forward end cap. So then, of course, the remnants of your, let's say, the pieces of your fragmentation, like pi zeros or multipions, they will actually go to the backward region, as we call it, in the detector configuration. So in both cases, there are signatures that we can detect in the forward region. So the definition of the forward physics is defined in the epoch is very loose, is that everything, if you have, let's say, a particle or signature detected by the forward end cap or the far forward region, they're all characterized as a part of the forward physics. That's kind of a bad definition, in my opinion. So it's a very loose kind of a bad definition. The only thing that is not in the forward physics category is the semi or the inclusive or the semi-inclusive region where the electron, of course, go to the backward end cap, and where you have a fragment of, let's say, a pion or something that reach the central region, where you don't care what is actually in the forward end cap or the far forward region. That is basically not part of the forward region. So yeah. So to answer your question, this really has to be getting into a kind of the part of the region where the semi-inclusive reactions where you don't require forward detection of the proton.
And I'm sort of thinking.
Yeah.
Any other questions?
So, Bill, I want to ask you about the limit of sort of quasi-real photon to real photon.
Yeah.
What's sort of the experimental status on that? Because
Yeah.
there've been tests of spin sum rules. For
Hmm.
instance, you can do photo production, measure GDH, and then really low Q squared like the EG4 experiment.
So the most interesting part is to explore the Q squared around 1 and a little bit less than 1. But then these are experimentally complicated at Jefferson Lab because you literally with 12 GeV beam have to put your detector almost inside of the beam pipe. That's not a goal. But then can we actually use some other collider type of experiment? There has been channel by channel basis as example. For example, in the pion form factor experiment, you can see that there is some very, very low Q squared measurement from, let's say, Andromeda experiment or something like that. But those are like not EP scattering. So the answer is that there is from some channels, we have some good low Q squared data. But if you say is there any Q squared data, full set of it to cover the entire range so we understand this quasi-real quasi-real limit better, EIC was supposed to do that. But the problem is that there is a hole, unfortunately, which I will show in the second part of the lecture, is that we likely won't be able to achieve that as well because of the detector layout constraints. Yes. You literally need to have a different kind of electron beam line in the backward region, in the far backward region to have a low Q square attacker perform better. So I can show some of the plot, yes. And likely that gap will be between 0.6 and 1.6 GeV, which is the really interesting part of it. Yes.
Yes, just maybe to follow up on this kind of question from the series viewpoint.
Yeah.
We very much like working in these additional frames like the bright frame of proton center of mass frame, which must be updated from the lab frame by boost.
Yes.
And the reason is that we can separate various radiative contributions better in those frames. Will it be easy to reconstruct those frames at the EIC?
So at the EIC, I think so. I think so. But the only complication that when we actually do this is why that this 25 milliradians crossing angle needs to be taken very seriously. So for, let's say, a naive, students that work on the project, he or she would automatically assume that, of course, this is the proton boosting direction. In that case, in some senses, yes, but there is a 25 milliradian crossing angle. So what this means, Pavel, is that we actually do this, is that how we actually get around it is that we will generate it in this frame, like Monte Carlo or whatever, the simulation that we run, then we then we turn this. We turn the reference frame by 25 milliradian by force. And that seems to be okay, but I don't know if we require, let's say, sub 1% difference than compared to the theory. I don't know if that'd be sufficient. It need to be tested. So we really need to, from the experimental side, also from the theory side, we really need to remember that this, like, it's not as beautiful as the CMS. There is a 25 milliradians difference in terms of the positive Z and also the proton eta infinite.
I'm sure that everybody's looking forward to our evening session. We are going to know the answer to the forbidden question.
Forbidden question, yes.
So forbidden question this evening.
Yeah.
But now let's go for lunch and thank you once again.